So today we are going to talk about the organic chemistries. And we have 5 items here. The second one is about review. So we are talking about the significance of organic pollutants in the environment. And then we'll talk a little bit about the structure or the properties of the chemical, because the chemical structure will influence the property of the chemicals, and the physical chemical properties will determine the partitioning of the pollutants. And then we're going to talk about the partitioning of the organic matter in different phases. So first, let's look at some leading environment pollutants. And here are we have the silt and we have the metals, especially for the heavy metals. And we will talk about this in the next unit. And we have the pathogens, and we also have nutrients, toxic organics, and the organic matters. And I think when I was young, I don't believe nutrients is pollutants. But now we know that if a environment has lots of nutrients, then the biodiversity will decrease. So this is bad for the environment. And we can also see that half of these leading environmental pollutants are related to organic chemicals. And for the organic chemical, it may be roughly classified into 3 types, that we are interested in. The first one is emerging contaminants, like the pharmaceuticals and perfluorinated acids and fragrances and the detergents. Also, we have the chemicals like they are persistent, bioaccumulative, and toxic. And many of these chemicals are POPs. And I will talk a little bit about POPs in the next slide. And this includes like PAH, PCB, PBDE, and PFOS, and some other like pesticides like DDT. And on the right side, I just want to show that we know that DDT is a pesticide and it is POP. And we know that this is a historically used pesticide and now it is banned. And here I just search for DDT and cancer. And this is a time range since 2018. So we can say during these 3 years, we still has lots of research about the relation between DDT and cancer. So I would say this is a very important topic. Another one is about the biogenic substances like the fatty acids and the sterols. So I want to talk more about POP because the lab I'm working on, or Dr. Torrance lab, is the POP lab, and this is a persistent organic pollutant research lab. Although this is different from my original designs, and I guess if I can find my original design. Yes, it should be here. So we can see that the logo of the whole structure of this logo is a POP, like it is a PAH. And then we can see we have the pollutants in the air, the pollutants in the soil, pollutants in the water. And in the soil, we have the pollutants in the earthworm or in the animals, and we have the pollutants in the grass or vegetations. So in this logo, I want to show that we are working on the POPs, and on the other hand, the POPs is distributed in all of the environments, from air to water and from animals to vegetations. So what's a POP? So POP refers to the organic compounds that are resistant to environmental degradations through chemical, biological, and photolytic processes. And they have some common properties, like they can remain in the environment of long period of time because they will not be degraded, and they can bioaccumulate in organisms because they are organic, and they usually have negative effects on human and animal health and the environment, so they are bad. And they usually become widely distributed through the environment. So we may find the POPs everywhere in our environment. And because of that, we have some agreements like these POPs are banned globally by us. But here when we have a question, if we know that these chemicals, they are bad, why didn't they get banned at the very beginning? So here I want to talk about a little bit the history of these POPs. And because I'm doing DDT and I'm familiar with that, I'm talking about DDT. So DDT is a pesticide, and here is a chemical structure. And DDT was widely used globally and in the United States in 1950s or 1960s. On the right hand, we have an attachment of DDT. We can see that. So this is an attachment. But I want to say that this attachment is very, very accurate. I mean, it can pass some of the information. We can say we have a baby here, and the baby is very happy and very healthy. So I want to say that this attachment indicates that DDT is very healthy, even for a little baby. So we can just use that at our home safely. Now it is get banned. And another picture is something like this. On the left side, we can see sometimes they are spray DDT, and it says that it is a powerful insecticide and it is harmless to humans. And on the right side, like the kids is staying in a film of the DDT. For now, they think this is very dangerous, but at that time, DDT was considered as not harmful. So they can do something like this. And because of the widely spread of DDT in the environment, we can imagine we have so much of the DDT stay in the soil or in the environment. And because of this, as the time goes, we find some negative effects of DDT. For example, someone finds the eggshell will be thinner by DDT, and this was published by a book, which is called The Silent Spring. We can say with the DDT, the eggshell of the birds is very soft, easy to crash. And as time goes, we also find that DDT can lead to cancer, as I showed of the Google Scholar page before. And except for DDT, we also have some other, like we find some other POPs that has a negative effects, and then some of the POPs get banned. So far, do you guys have any questions? If you guys have any comments, you can just post it in the chat. The next thing is about the structure and the functional groups. On the left side, there are some common functional groups of the organic chemistry, and the most common one I would say we have 4 here. So what are the functional groups? A functional group is a special cluster of atoms that performs as a useful function. And the most of the useful behaviors of the organic compounds comes from the functional groups attached to the carbons. And so let's talk about them a little bit more. And the first important one is hydroxyl groups, which is -OH. I'm not going to talk details about that. So if you guys forgot this one, you may just do your review. But here I just want to say that OH usually does not dissociate H+ in the water, but except for phenol and carboxyl groups. So the phenol can dissolve in the water. And the most important point is that hydroxyl group can make small organic molecules soluble. And on the right side, this is the picture of phenol, and this is a picture of phenolphthalein. Another one is a carboxyl group, which is -COOH. So there are some properties. A carboxyl group usually dissociates H plus in water, so they can perform as acid. And again, the most important point is this: carboxyl group can make organic molecules soluble, and they can dissociate H plus like here. And on the right side, there are some common organic acids. The last one is amine or amine group. And again, amine can combine H plus and perform as a base. So it can become charged like shown here. And because it can become charged, it is soluble in water. So amine can make organic molecules water soluble. So far, do you guys have any questions? Yes.
I assume you would actually mix these in the water.
Excuse me?
Would you add these additives to the solution and then that chemical reaction would happen in the aqueous state?
Oh, so they are not additions, like they are attached to the organic matter. So they are part of the structure of organic matter instead of they are like the chemicals added to the solution. So any more questions? Oh, okay. So let's about the partitioning of the organic matters. The first one is partitioning between pure phase and air. So, and the parameter is vapor pressure. So, vapor pressure is defined as the pressure exerted by a vapor in a thermodynamic equilibrium with its condensed phases, like the solid or liquid, at given temperature in a closed system. And the keyword is equilibrium. So it must be in equilibrium. And the vapor pressure controls the concentration in the air in equilibrium with the pure phase. And it usually increases with temperature. So basically, with higher temperature, we would expect more molecules and become in the air. And in summary, vapor pressure describes the ability of the chemicals to fly in the air. And on the right side, it just shows some of the chemicals that change, like the chemicals that have different vapor pressures. And from this picture, we can see that usually the smaller molecules have a higher vapor pressure. In other words, the small molecules, they are easier to fly or to evaporate in the air. And for this one, do you guys have any questions? And here we have a calculation question. So let's just say in a factory in which the metal parts are degreased with organic solvents, and someone drops a glass container that contains 10 liters of this trichloroethylene, chlorosine, TRI, in a closed room at 20 Celsius degree, and the room has a total volume of 50 cubic meters. So basically, this is not in the lab. We know that in the lab, we have the fume hood, so the air will be evacuated. But for some of the rooms, they do not have that ventilation system. And the bottle breaks, and the solvent mixture spills on the floor, and soon one can smell the solvent vapor in the air. And here is the chemical structure of trichloroethylene ethane. And now we want to know that do we need to evacuate the people in the room? And to answer this question, we can split this question into several small questions. So the first one is, what processes are involved in this event? Do you guys have any ideas?
Some of the liquid chemical is
But when you enter the screen, you have a assumption that this is a liquid. Yeah, but intuitively it's correct. So yes, we have some chemicals spilled in the room and then it will evaporate in the air. Then we want to know, to answer this question, what information do we need? To answer this question, do you guys think? So first we need this. Yes, so to quantify how dangerous it is, we may need a parameter, and we talk about this as a toxic reference value, like in the lab form. So we need to know its toxicity reference value. And do we need other more information? Yes.
It's concentration.
Its concentration
Inside the room.
inside the room.
Yeah.
Yeah, so this is exposure. And we can calculate hazard quotient equals to the exposure divided by TRV. And then if HQ is greater than 1, then we need to evaluate.
Sorry, TRV is what?
Toxicity reference value. And so we want to know the exposure, but this is unknown here. Do we need any other information to calculate this, to know this exposure, like the concentration of TRV in the room? Do you guys think what information do we need?
Like the molecular weight of TRV?
Yes. And then any more information we need? Good.
Okay.
Yeah.
Pressure in there?
Yes, like, but we usually assume the room is 1 atm. And a key parameter we didn't mention.
Henry constant. We got Henry constant. We also need the area of the spill.
Yes, we have the volume, and because this is the
One of the area of the spillage for the double phase.
area. I think the area
Or are we
will be,
looking at it at the equilibrium?
yes.
Oh, okay.
Yeah, so that will be in equilibrium. And another one is, I would say, the vapor pressure of the chemical. And another thing is the state of the chemical, because we even don't know the state of the chemical. So basically, we need to know its boiling point and the melting point. So we need to know what's the state of this. So, and another question is, where can we find reliable information? Because we find we need some information, but now we don't have any information. So where can we find this information? And I think on Wikipedia we can find some information, but for me, I usually find the information on this site, like the PubChem. And for the PubChem, we can find the information of different chemicals. We can see on the right side, the table of contents, like it has its general properties, and it also has the safety and hazards or toxicity. So we can find the toxicity information of this chemical, and we can see we have different values, but that doesn't matter. So here, let's just say we find some information on the left side. And to be simple, I just choose the easiest one. So the toxicity reference value, let's just say equals to 8% of its separation at its saturation limit. And here we have the molecular weight. Oh, we also need the density because we only know the volume and we want to know the mass. And we have the boiling points and melting points and the vapor pressure. So to answer this question, first, we want to know the moles of TRV in the that we have. So we can calculate the moles of TRV. And then we want to know that, let's just assume or what are the amount of TRV that is needed to make this room saturated. So We know that the concentration equals to the vapor pressure divided by this value. And this comes from this ideal gas law, and we know that concentration equals to N divided by V. And then we can calculate the saturated, like when it is at saturation, what is the concentration of TRV in the air? And then we just plug the number into this equation and we can get this value. So this is the concentration of TRV if this room is saturated. So we can see that the moles of TRV needed to saturate the room equals to the concentration times the volume, and it equals to this mole. So in other words, we want to make sure this room is saturated with TRV. We need this amount of TRV. But in reality, we only have this amount of TRV. In other words, all of the TRVs will be evaporated in the room. So no one will stay on the ground. And also because this amount is larger than 8% of this amount that is needed to make the room saturated. So evacuation is needed. Or in other words, we can calculate the concentration of TRV in the air. It equals to the amount of TRV that we have, and we know that all of the TRV will get into the air. So the concentration will be this one. And so for this one, do you guys have any questions? Yes.
What's the purpose of the 8% again?
Oh, this here. Because the toxicity reference value equals to the 8% of the saturation at its limit. So, like, it's in other words, when it's at saturation, we have the N moles of TRV. Now we need to know that we have 8% times N is the limiting moles that we have in that we have. Yes. So any more questions? Okay. The next one is about aqueous solubility. And sometimes we use ACE to specify it, but to be more accurate, we can use CWSAT. And this describes the partitioning between pure phase and the water phase. So aqueous solubility is the concentration of the chemical in the aqueous phase, and when the solution is in equilibrium with the pure compound in its usual phase, like the gas, liquid, or solids, as a specified temperature and pressure. And in the environment, we usually assume it is at 20 Celsius degree and 1 atm. And the aqueous solubility is moderately temperature dependent. And in environmental engineering or science, we would say insoluble or sparingly soluble are inaccurate, because we would say everything will have its aqueous solubility, but its solubility may be very small. And also, the aqueous solubility is determined by whether a organic compound likes water or dislikes water, or it's hydrophobic or it's hydrophilic. And this property is strongly determined by its functional groups. So basically, if we have some of the chemicals that has the functional groups of hydroxyl group or carboxyl group or amine group, we would expect that it will have relatively high solubility. So in summary, aqueous solubility describes the ability of the chemical can stay in the water. And on the right side, we have the solubility of different chemicals. And from this plot, we can see that generally we have the smaller molecules usually have a large solubility. But large chemicals, they usually have smaller water solubility. And for this value, that's question. And here I want to emphasize that we see that this is moderately temperature dependent. We didn't mention it's increase or decrease this temperature. This is because, like this is in general, we have some, like this example. This is for inorganic matters, but I just want to show the concept. So basically, we can see that for some of the chemical, this is solubility and this is temperature. We can see the solubility increase with temperature, but for some chemical, the solubility decrease with temperature. And for some of them, this is a little bit different. So I would say temperature will influence solubility, but the influence is not quite sure. And so for this one, you guys have any questions? The next one is about the partitioning between air and water. And this is described by Henry's law constants. And I think we have mentioned it in the alkalinity lecture. So Henry's law constant refers to at constant temperature, the mass of a gas dissolved in a given volume of a solvent is directly proportional to its partial pressure in the gas phase in equilibrium with the solution. So in other words, the partial pressure of the gas and the concentration of the chemical in the water, their ratio is a constant. And it also emphasizes that they should be at equilibrium. And based on this equation, let's just say, what does the larger KH mean? What does the larger KH tells us? Yes. Yes. So
Volatility.
yes. So I would say the larger KH, it means that it prefers to stay in the air than stays in the water. And on the right side, we have the different chemicals of, like we have the chemicals of different KH values. And so from this picture, what general trend do you guys find? So what do you find in this picture? And this is the KH values.
Maybe smaller compounds have higher pH values.
Like this one, right? Like this. But we still have some. We have someone like this. We can say C5 is in the middle, and we have like different sides. So we can see that for the KH values, this is a little bit different from others, because also for this one and for this one, we can find that for the smaller molecules, they are in the middle, but for larger molecules, they are on the two sides. Why this happened? So I just did some little research about this question. So in this table, I just find the KH values of different hydrocarbon, like from C1 to C18, and I find the pH values from different sources. And then we can make a plot. So this is a number of carbon, and this is the KH values. Note that this is in the log plot. And from this plot, we can see that it may increase and decrease and increase, and then decrease, increase. It will be something like this. So we do not have a general trend of the KH values. And why this will happen? So I think my explanation is that we can see that for the CX, like X refers to the number of carbons. As the number of carbon increases, or in general, the molecule becomes larger, it will be less soluble. So the solubility will decrease. And as the molecule become larger, it will be less volatile. So the vapor pressure will also decrease. And we also know that at saturation of the two phases, Henry's law constant equals to the vapor pressure divided by its water solubility. And we know that as the X increase, both of them will decrease. So which one is dominate affects the change of the KH value. So I would say, so the KH value is influenced by both of these two parameters. That's why the small one has the middle, is in the middle, and we have some large ones at different sites. So for this one, do you guys have any questions? No. Okay. The last one is octernal water partitioning coefficient. This is a parameter describing partitioning between organic solvents and water. So octernal water partitioning coefficient represents the ratio of the concentration of a compound between two phases at equilibrium. One is the octernal, and the other one is water. And it can be described by KOH equals to the concentration in the octernal phase and the concentration in the water phase. But make sure they are at equilibrium. So this chemical, this parameter is the most common way of expressing the resolvability of a compound. Why? Because, so let's just say for a large KOW value, what does it mean? You guys wanna?
Concentration of the chemical in octavals higher.
Yes, and it can also tell us that this chemical is preferred to stay in organic phase rather than the water phase. That's why this can be an indicator of the lethophilicity or hydrophobicity. And here the chemical structure of octernal, and the properties are pretty similar to the fat in the human beings. So we use this as an indicator chemical to describe its properties. And for this one, you guys have this.
So when we're saying the concentration of the chemical in water, like in the picture there, when it's just octanol, it's like, you know, more solid phase, or I guess like what does it mean for it to be in water exactly? It's just down to the water, so it's kind of dissolved.
Yes. So let's just have two examples. The first example, let's say DDT. So, like, let's say this is water and this is octernal. So the DDT will have the concentration in the water, and DDT will also have some concentrations in the octernal phase. So in this case, the KOW equals to the concentration of DDT in here divided by the concentration of DDT in here. So this is a concentration inside these two phases. Yes.
And can the DDT move between those two phases to reach equilibrium across that
Yes.
threshold?
So if at the very beginning we have the DDT here, and then it will just spread to here, like that, yeah, and then it will reach equilibrium. And on the other hand, we may also have another case. For example, we have like CH3, CH, let's just say we have N and COOH. And we have this one, and we know that this one will be dissociate into like CH3, CH, COO minus plus H plus. So in this case, it will dissociate. So in this case, we only consider the part of this chemical that does not dissociate. So when it dissociates, we do not count it. Does this make sense? Because when we have this chemical in the water, some of them will be dissociated and become charged, and some of them will not dissociate. They will just remain itself. So when we are calculating the KOW of this case in the water phase, we only consider the concentration of the undissociated part. So any more questions? Here's the summary. If we know the partitioning coefficient, and the partitioning coefficients can usually be determined by the experiment, and know the total amount of the pollutants released in the environment, and they usually released in only one phase. And then we can calculate the pollutant concentration in each phase when it is in equilibrium. So like we have different phases here, and we also know the different partitioning coefficients between different phases. So we can calculate the equilibrium concentration of the chemical at different phases. And here is just an example. So on the left side, we have the table of the chemical of different properties. We can see, like, for example, we have the DDT and we have different other pesticides. And here is a chemical structure, and here is a water solubility. And this is a log KOW. Because the KOW may be very large, so we sometimes use a log KOW to express this. And we also know the vapor pressure of the chemical. And sometimes we know the molecular weight. So let's just say for this DDT, given these different parameters, what do we expect DDT? Like which phase do we expect DDT to have the high concentration in the environment? Let's say we have the water, we have the air, and we have the animals and plants. So which phase do you guys think we expect to have the DDT has a higher concentration? Based on these values that they have.
This might be a silly question, but what's the vapor pressure of water at 25 degrees C?
Oh,
I
you mean
need like some context for what that value means.
can you say that again?
Do you know what the vapor pressure of water is at 25 degrees C? I'm trying to get some context for whether that's a high value or a low value.
Oh yeah, that's a good point because we do not have any comparison with other stuffs. Yeah, that's a good question. I'm not sure, but the water vapor pressure in the air. Yeah, I'm not sure. Any of you know? Yeah, that's a good question. But I would say intuitively, this is small because this is -7. But I guess I will take a look at what's the vapor pressure of air, of water in the air. But that's a good point. We need reference. But on here, let's just look at these two values. We have the solubility, and again, we do not know the solubility of some reference chemicals, so it is also hard to determine. But we can also see that for the log KOW, this is greater than 1, which means the KOW equals to like 10 to -7. So even though we cannot compare the absolute water solubility with other things, we can predict that when DDT dissolves in water, it will quickly leave the water to the organic phase. So we would expect that at least between these two phases, we would expect that DDT will prefer to stay in the biota or in the organic phase. And so for this one, do you guys have any questions? No? Okay. Yeah, that's a good point for vapor pressure. And based on my experience, I would say that PET has a relatively low pressure. Because we can say this is pretty large. And for the water molecule, it is relatively small. And in general, this would expect to have much lower vapor pressure than the water. But we need to confirm that. Okay, so here the summary. Because of time, I'm not going to go through this. And here is a note. And so on Thursday, we are not going to have class. And the deadlines for assignment 5 and the quiz 7 will be the end of this month. And that's it for today.
Remember, could you go back to the last slide?
Yes. This one?
No, one more, the one with the professional and stuff. Do you know, like, I'm thinking of for a reference point for solubility, I'm thinking of salt as being like one of the most soluble things.
Yes.
Do you know what that value, is that like
I think
two,
it's 100 or 200.
oh, like several orders of magnitude larger than?
Yeah. Or at least we can. See.
Like, I guess, water and alcohol.
I know alcohol is miscible, yeah. So
And it will always.
yeah, they can
dissolve.
mix as any ratio. Yes. So the
Why is that like 50%?
okay. What's the solubility? Oh, I cannot use control plus F to find the value.
It's right under 3. Yeah, you're in the right category. A little lower. So
Oh yeah, solubility.
36 grams.
Oh yeah. Like it has 63 gram, which means it has 300. Yeah, 63. In the meanwhile, we can see for the DBT that is much smaller, and this is milligram.
That's nearly Jesus.
Yes. Yeah.
So I know that we have like the KOW value up there.
Yes.
And because that was greater than 1, we knew it was for the organic phase.
Yes.
And then how did we eliminate like the gas phase, or is it, yeah, how did we say it wasn't
In gas phase.
or is that wasn't an option?
Some of them can be get released in the gas phase, and we may also assume there's a water. Like we have the organic phase here, and we have the water phase here.
Yeah.
And the organic phase is in equilibrium with the water phase, and the water phase is in equilibrium with gas phase. So we can use this to calculate its like corresponding concentration in the gas phase.
And what value did you use? Or we use just the
So in here, like they have the KOA, like the partitioning coefficient between organic phase and air phase, but I rarely see these values in practice. Yes, and I would also say usually we do not, like for the organic pollutants, because they prefer to stay in organic phase. So I would say they do really come from the organic phase to the air phase.
the table that we were just looking at, do we have the KH value?
No, we do not have the KH values here. Yeah, but for some other chemicals, we can find the KH value. Oh,
By just looking at the vapor pressure, are you able to tell it won't go to the gas phase?
Yeah, I think this is a good question because we do
Or
not
that's
have
what
a
you guys
reference.
found.
Yeah,
Okay, thank you.